Hello everyone, the Teen Engineer here, and today we're going to solve a torque problem. So first off, let's read it. A painter wishes to know whether or not he can safely stand on a ladder. The ladder has a mass 11 kilograms, which is uniformly distributed throughout its length, 7.8 meters. The ladder is propped up at an angle theta equal 46 degrees. The coefficient of static friction between the ground and the ladder is 0.5, and the wall against which the ladder is resting is frictionless. Calculate the maximum mass of the painter for which the ladder will remain stable when he climbs up a distance d equal 4.6 meters up the ladder. If the painter does not stand on the ladder, what is the minimum angle theta for which the ladder will remain stable? Okay, well, first off, when we work with torque problems, we should always draw the isolation. Well, first off, let's complete the drawing. So I'm just going to make that bigger. Right. So let's draw that. Okay. And we have that. We have this angle here. This is 90 degrees, let's see. And let's draw him as a ball or something, just to make it easier for us. So this is the painter here, and he is a distance they say 4.6 meters. There is, well, the whole ladder is 7.8 meters, and that will be pretty much all we need here. So now let's draw the isolation diagram. Let's draw an isolation diagram. So I'm just gonna draw it here. Move all of this. Oops. Move all of this. Move that there. Oops. I'm just gonna lock this. Okay. All that. No. Okay, one last try. Draw all that. Okay. Now it should be fine. So let's draw an isolation diagram. So let's make that here. We have we're just going to draw the ladder. So I'm just going to also draw the angle here, theta. Now in the isolation diagram, we basically draw all the forces. So the first force here is, I'm just going to call that N2. It's the normal force from the wall onto the ladder. Now we also have the weight of the painter. Weight of painter, I'm going to call that WP. We also have the weight of the ladder itself, WL. And at the bottom we have the ground pushing up on the ladder, so I'm going to call that N1. And we also have a frictional force that they talked about, which is Fs, I'm going to call. Now, we have to define their axes, so I'm going to define it as being clockwise is positive. Clockwise is positive. And we also have to define our origin. Now, since there is no like hinge or anything like that, you have to define your own origin. So you can either choose one of the extremities, but the better way to do it would be to choose one which has the most forces to eliminate them from the torque. Since if there's a force on the origin itself, then the torque is zero. So you want to place the origin where there's the most amount of forces, which could cancel out. So I will place it here, since we cancel out the N1 and the Fs. They would both be, the torque of these forces would be zero, which facilitates their lives. So that will be pretty much the isolation diagram. Let's just, I'm going to write the distance here from each of these forces. I'm just gonna write the distance. So this one is at the, so this one would be 0 here, since it's the origin. So this one would be 7.8 meters away. The painter is 4.6 meters away. The weight of the ladder is always, like when you have the weight of something, it's always at the middle. So 7.8 divided by 2 would be 3.9. So weight of the ladder is at 3.9. And that will be pretty much all we need here. Now, to simplify our lives, I'm also going to draw the angles. So since theta is, they gave it to us, 46 degrees. So if we can imagine a triangle here, a right triangle, so this angle up here would be 90 minus 46, which is 44. And since weight of the ladder and weight of the painter are parallel, then they are the same angle, so 44 degrees. Now the N2 is alternate angle with 46 degrees, so that's also 46 degrees. So yeah. So this will help us find the perpendicular angles, which we'll need later. So let's also draw a free body diagram. Might as well do it now. So I'm just going to do it over here. Wait, might as well do it nicer than that. Right. So I'm just going to write X here, Y here. Now, all the forces have to be on this diagram. Even if they're on the origin, they still matter. So we have N1, we have frictional force, we have the weight of the ladder, we have the weight of the painter, and we also have the normal force of the wall onto the ladder. So now that's all done. Let's work on finding the maximum mass. So what I'm going to do is take that here, try and take everything so we can move it somewhere else. Oops. So I'll copy that. Here it is. So now, since the ladder isn't rotating or moving, we can assume that sum of torque is equal to 0 and sum of forces is equal to 0. So we need to assume that. So now, let's start with torque. So the torque of let's do a different color. Torque that the force of the ladder, of the weight of the ladder exerts. So I'm just going to say torque of the ladder is equal to the force itself, so the weight of the ladder, times the distance from the origin, so here is 3.9 meters, times here it will be, we need to find the perpendicular force. So we need to multiply that by sine of 44. Since sine of 44 would be this perpendicular force, that's what we need. So it's not the force itself, but the perpendicular force. We also need to make sure that this is positive because it's going in the clockwise direction. Oh wait, no, it will be going anti-clockwise, so I have to make that negative. So we have to be careful here because it's related to the origin. So how to know if it's positive or negative is if you look at how you define your axes, if that would be the only force there, if the weight of the ladder would be the only force, then you have to imagine which way the ladder would go. So if the weight of the ladder would be the only force, it would be pulling it in the counterclockwise direction, which is the negative direction. So that's done for the torque of the ladder. Now let's do the torque of the painter exerts, and that's also negative. That's his weight of the painter times the distance of 4.6 meters, and here is again sine of 44 to get the perpendicular force. And now finally the torque that the normal force exerts. Torque of normal force, that will be N2. And this one is positive because if it were just to be the only force there, it would turn it in the clockwise direction. So it would be positive. So that's N2 times 7.8 meters times, and then to get the perpendicular force, we have to do sine of 46. All right. So now we can, let's move that a bit. Now, sum of torque is equal to 0, but it's also equal to torque of the ladder plus torque of the painter plus torque of normal 2. So it's equal to 0, but the sum of torque is equal to the sum of all torques that we have. And those are the 3 torques that we have. So let's replace it. Let's replace all of them. So it's this one. So torque of ladder is W. Well, actually, let's just simplify our lives here and just copy those. Yeah. Whoops, forgot something. So lasso tool, everything. Let me just fix it up real quick. It's minus. And then also take that. Everything here. Okay. I'm going to need to get everything here. Right? Right. Yeah, that works. So, yeah. And then finally, the last one. Copy, paste. Oops, still didn't copy it. Delete. And should work now. Right? Okay. Now paste. Cool. So, let's move out. Lasso that. Everything here. Okay. Paste. Got it. Cool. Let's move out the way. Whoops. let's move that out of the way. Okay, good. And now just select that one, take it and put it there, and just add that. Okay, good. So plus, okay. So now that we have all those, we can, let's simplify everything to the lowest form. So the weight of the ladder, we can change that into the mass times 9.8. So that would be negative, and then mass of the ladder times 9.8 times 3.9 meters times sine of 44. And then do the same thing for the others. So minus mass of the painter times 9.8 times 4.6 meters times sine of 44. So this equation is getting really long, but it's going to get simplified a lot. So, and then plus this one, we can't really do anything with it. So N2 times 7.8 meters times sine of 46 degrees. Sine of 46 degrees. Now, I'm just going to multiply everything that we can so we can simplify this equation. So first one, so that would be 9.8 times 3.9 times sine 44. Okay. That's negative 26.55 mass of the ladder. And then this one would be 9.8 times 4.6 times sine of 44 minus 31.32 times mass of the painter. I just realized we might have the mass of the ladder. Did they give us the mass of the ladder? They did, 11. So let's remove this, and that's minus 26.55 times 11. That'll be negative 292.05. Negative 292.05. Negative 292.05 minus 31.32 times mass of the painter. And then that would be 7.8 times sine of 46. So plus 5.61 and 2. So now we have two variables. We can't really solve this. So that's why we need these static equilibrium, translational static equilibrium. So sum of forces is equal to 0, which is what we'll do right now. So let me just bring that over here. All right. So we have that. And now, since the sum of forces is equal to 0, we can do two equations out of those. So sum of forces is equal to 0, which means that sum of forces in x is equal to 0, and sum of forces in y is equal to 0. Whoops. Sum of forces in y is equal to 0. Now, sum of forces in x, we have N2 minus static friction. That's equal to 0. And here we have, in the y, we have N1 minus weight of the painter minus weight of the ladder, and that's equal to 0. Now let's work with the x first. So N2 is equal to 4 frictional force. And then that means that N2 is equal to mu S times N1. So frictional force is equal to the coefficient of friction times the normal force. Now in this case, the normal force is normal force 1 here, and the the coefficient of friction is 0.5. So this means that N2 is equal to 0.5 times N1. All right. So let's have a look now at the Y, forces in Y. So N1 is equal to, we just put these on the other side, bring these to the other side. So N1 is equal to weight of the painter plus the weight of the ladder. So N1 is equal to weight of the painter. Weight of the painter was how much? We need to find that, and the ladder was 11 kilos. But what I'm going to do is separate it into the mass. So this is mass times 9.8. And then the ladder is 11 times 9.8. And that's equal to 11 times 9.8, 107.8. So that's mass of the painter times 9.8 plus 11 times 9.8 plus 107.8. 107.8. Now that we have this, we have the N1 with respect to the mass of the painter. We have N2 with respect to N1. And we also have an equation here with the mass of the painter N2. So what I'm going to do here is replace N1 in the equation N2 is equal to 0.5 times N1 by this equation here. And then we're going to replace that in this equation here. So what we're doing is just here, taking this equation and plugging it into this one. So let's do that. So N2 is equal to MP times 9.8. I'm going to put it as a fraction, but it will be easier for us over 2. Over 2. And then we're going to replace that into the final equation, which will allow us to find. So this, we're going to plug that in to this one here. And then it would leave us with only one unknown variable, which would be mass of the painter, and we will solve that. So let me just bring this equation out. Bring this equation out. Oops, I forgot to include the 2. Alrighty, paste that. Here it is. We have that here. And the n wasn't included, so let's change that. Okay, now let's plug that in. So 0 is equal to negative 292.05 minus 31.32 times mass of the painter plus 5.61, and now times, let's bring a parentheses here, and let's just copy that. So mass of the painter times 9.8 plus 107.8 over 2. I was going to make that nicer. 7.8 over 2. All right. Now let's simplify all that. Negative 292.05 minus, whoops, forgot to make that, minus 31.32 times mass of the painter and now I'm just going to multiply. So 5.61, we're going to divide that by 2 so we can remove that fraction, and we're also going to multiply, so that would be 2.805, and then we have to multiply that, so that would be 2.805 times mass of the painter times 9.8 plus 107.8. Now I'm going to just copy all that, copy everything, bring it here, just change the last part. So we're going to distribute 2.805 2.805, going to distribute that, so here and here, so 2.805 times 9.8, that is 27.49 times mass of the painter plus 107.8 times 2.805, and that is 302, so 302.38. All right, so let's add these two together. So minus 292.05 plus 302.38, that would be, so we're just adding these together, so that would be 10.33 minus 31, wrong color, minus 31.32, and oh yeah, let's also add the mass of the painters together, these two together, so 27.49 and minus 31.32, that will be minus 3.83 mass of the painter. And now let's just do some simple algebra here. So 3.83, which would give us mass of the painter is equal to 2.70 kilos, which is not much for a human. But let's see. After all this, that's right. Now, second question. If the painter does not stand on the ladder, what is the minimum angle theta for which the ladder will remain stable? So let's continue. Now it will be basically the same thing except one less force. So let's just, if I take this, all that, let's just copy that. So we're just going to remove one force, so make it a bit easier. Do it here. Make that a bit bigger. Okay, so we can remove the weight of the painter now. Remove that, remove this. Okay, so let's just do the same thing again. Sum of torque is equal to 0 because it has to remain stable. Torque with due to weight, we already calculated that. That was, we calculated it over here, so minus 292.05. So let's just copy that again. So torque due to the weight of the ladder is equal to minus 292.05. And now we have what other torque? We have the torque due to N2 is equal to, we don't really know this one, but we can try and, let me just change the color. So torque due to N2. And this one would be force of N2 times 7.8 times, and then there would be times sine of the angle that we will choose. So times sine of theta. So now we have two unknowns again. Now let me just put it into the sum of torques formula. So 0 is equal to negative 292.05 plus the torque due to N2, which is plus N2 times 7.8 times sine of theta. All right. So now to find N2, we already have the relation. We already have the relation between N2 and N1 over here. N2 is equal to 0.5 times N1. That doesn't change. The only thing that changes is the angle, but in this case, it doesn't really matter. So as we can see, N1 is equal to mass of the painter times 9.8 plus 11 times 9.8. This is the we found this with the free body diagrams. So this doesn't change. So we can plug that back in to the what we can do, yeah, now that we have the the painter, if the painter does not stand on the ladder, what's the minimum angle? Okay, so actually I need to redo the free body diagrams for simplicity. Let's do it again. Let's take that, copy that. So let's do the free body diagrams again, because we have two unknowns here, so that's what we should think of. I'm going to remove the weight of the painter. All right, so now let's do that again. So sum of forces is also equal to 0. Sum of forces in y is equal to 0, but that's also equal to N1 minus weight of the ladder. And then sum of forces in x is also equal to 0, but that's also equal to N2 minus frictional force. Now this means that N2 is equal to frictional force. We just bring frictional force on the other side, and frictional force at the max is equal to mu s times the normal force, and the normal force is N1. So this would be mu s is 0.5, so 0.5 times N1. Same thing as before, but the thing that changes is this one. So this equation, so this makes that N1 is equal to weight of the ladder, and weight of the ladder is 11, so this will be 11 times 9.8, 11 times 9.8, so that's 107.8, 7.8, and then we just plug that back in here, divide that by 2, so this would be 53.9 newtons. So now that we have this, we plug it back in here, and then we isolate for theta. So this will be 53.9 times 7.8, then negative 292.05, divide that here. Then take the inverse sine. So N2 is 53.9 times 7.8, and then we have 292.05. We take that on the other side, we divide that, and then we take the inverse of the sine, which gives us 44 exactly. So let's have a look at the answer. Whoops. So after all this, we have a look at the answer. And it's very small, but let's see. 45 degrees, so this is rounded up. So yeah, that's pretty much how you solve this problem. So if you like this video, then give it a like, thumbs up, and subscribe. Goodbye.